Good day, I bid to Dr. Siva and my fellow classmate. We are from Group 5, which consists of Afiatul, Ahmad Aiman Shah, myself, Arlene, and also Saradia. Today, we will be presenting the Open Lab of Process Control and System Modeling. In process industry, maintaining the right temperature is crucial, especially for operation like energy optimization, sterilization, and chemical reaction. Inaccurate temperature control can lead to product defect and waste energy. A heated tank is a common solution. It's widely used in the industries like food manufacturing, pharmaceutical, and chemical processing, where we must ensure the outlet fluid temperature remains consistent even when the inlet temperature of flow rate changes. The heated tank operates as a continuous stirred tank heater. This means it continuously mixes and heats the fluid inside the tank. In these experiments, we focuses on four main objectives, which is to model the heated tank system based on energy balance. Second, to derive transfer function using Laplace transform. Third, to stimulate its behavior in both open loop and closed loop configuration in MATLAB. And lastly, to design controller including P, PI, and feed-forward strategies to improve its performances. Ultimately, we aim to understand how controller tuning affects system behavior, especially in terms of maintaining the set points and rejecting disturbance. Now let's look at how the heated tank system works and how we model it. A fluid enters the tank at a certain inlet temperature, which can vary depending on process condition. The fluid is continuously stirred and heated inside the tank using heat source such as electric coil or steam jacket and exit at the outlet temperature, which is the control variable. The main variables in this system are tank volume, inlet temperature, outlet temperature, flow rate, and heat input. And several assumptions are made, which is perfect mixing, constant fluid properties, no heat losses, and single phase system. Using the assumption that we made, we applied an energy balance to derive the system dynamics. This gave us a first order differential equation, which we then converted into the Laplace domain to obtain transfer function. This equation model how the outlet temperature responds to changes in heat input and serve as the foundation for designing our control strategy.
Assalamualaikum Berhai. I am Afiatul Mundira binti Macharin, the second presenter from Group 5. Today I will present part of our process control and system modeling project. To model the system, we apply the first law of thermodynamics. The rate of change of internal energy is equal to the net in heat input. This leads to the energy balance equation shown here. After simplifying by dividing both sides by rho CPV, we obtain the first order ordinary differential equation. This equation describes how the outlet temperature changes over time depending on both the inlet disturbance and heat input. So function as shown here. One for the manipulated input Qt, giving us Gp, the process transfer function, and one for the disturbance Tin, giving us Gd. Both share the same denominator, indicating a common time constant. This time constant tells us how fast the system responds to input or disturbance changes, a key factor in controller tuning. These transfer functions are used in simulating to simulate system behavior and evaluate controller performance. That concludes the modeling and derivation section. This model allows us to implement and tune controllers to maintain temperature despite disturbance.
On this slide, I'm showing how I derived the characteristic equation of the closed-loop control system based on the open-loop transfer function. First, I assume the controller is proportional only, so Gc equal to Kc, and the valve dynamics are Gb, where 1/2s plus 1, and the next one is the process and disturbance dynamic, where Gp equal to Gd equal to 1/4s plus 1. The measurement or sensor dynamic are Gm, where Gm is 1/s plus 1. I use the standard closed loop formula, which PV over SB equal to open loop over 1 plus closed loop, where the open loop gain is the product of the controller, valve, process, and sensor. Substituting in all transfer function, the denominator becomes 1 plus Kc times 1 over 2s plus 1 times 4s plus 1 times s plus 1. Multiplying out the denominator and we get the characteristic equation as shown in the slide. This final characteristic equation is key because its root determines system stability. I later use to find ultimate gain and ultimate period for tuning the controller. This slide shows the open loop simulation model I used to study the process dynamics and to identify the critical gain and oscillation period for control tuning. In this setup, I apply a step input of magnitude 1.0 to the manipulated variable at 10 seconds and a disturbance input of magnitude 0.5 at 40 seconds. This input passed separately through the process transfer function GP and the disturbance part GD. The two outputs are then summed and displayed on the scope. This simulation helped me to observe the natural response of the process without feedback, understand how the process responds to both input and disturbance, use the oscillation behavior to determine the ultimate gain Ksu and ultimate period Pu when testing under proportional only control in open loop. This slide shows the simulating model I developed to stimulate the closed loop control system using the Ziegler-Nichols tuned PI controller. Let me walk you through this step. First, the set point introduces a step input of 1.0 at 10 seconds representing a desired change in the process variable. Second one is the controller block is a PI controller tuned using the Ziegler-Nichols method with the parameter I calculate. The controller output is passed through the warp dynamic model as GV, then it enters the process transfer function GP. The system also includes a disturbance input of 0.5 at 40 seconds which pass through the same process block GD before affecting the output. The output signal is measured through the sensor block GM and this feedback is subtracted from the set point to form the error. Finally, all signals are sent to a scope where I monitor the process response to both the set point change and the disturbance. This model allows me to evaluate the performance of the controller including rise time, overshoot and disturbance rejection under realistic conditions. The first tuning rule I use is direct substitution method to determine two important values, Ksu, the ultimate gain, and Pu, the ultimate period. We start with the characteristic equation where I get 8s power of 3 plus 14s power of 2 plus 7s plus 1 plus Kc equal to 0. Now we substitute s with j omega. We use complex number rule which is j power of 2 equal to negative 1, j power of 3 is equal to negative j and j is equal to j. After simplify, we get two parts which is imaginary part and a real part. For imaginary part, I get negative 8 j omega power of 3 plus 7 j omega equal to 0, and for the real part I get is negative 14 omega power of 2 plus 1 plus Kc. Now we solve this one by one. We start with the imaginary part. We set it equal to 0 to find the value of omega where the system begins to oscillate. So the omega I get is here is 0.935. Now that we know the omega value, we plug it into the real part. Negative 14 multiply with 0.935 power of 2 plus 1 plus Kc, and solving this give us the ultimate gain which is Ksu 11.24. Next, we calculate the ultimate period using the formula Pu equal to 2 pi over omega and we get 6.72 seconds. To summarize, the ultimate gain value we get is 11.25 and the ultimate period Pu is 6.72 seconds. These values are useful for controller tuning, especially in method like Ziegler-Nichols. The second tuning rule I use is Ziegler-Nichols tuning method to determine the controller parameter for P and PI controller. Based on the value we calculated earlier, the ultimate gain Ksu is 11.24 and the ultimate period Pu is 6.72. For the Phi only controller, we use the formula Kc equal to 0.5 times Ksu, which gives us Kc value is 5.62. For the PI controller, the gain is Kc equal to 0.45 times Ksu and we get 5.62 0.06. We also calculate the integral time for Pi, which is Pu over 1.2 equal to 0.6. To find the integral mod I, we use the formula I equal to Kc over tau I equal to 5.06 over 5.6. Estimately we get 0.9. This value will help us tune the controller effectively for stable and responsive system behavior.
Hi, my name is Sarah Debinti Maktudin and I am the fourth presenter for this group. I will present result, discussion and conclusion for this experiment. In the open loop configuration, the heated tank responds to changes in the input without any corrective feedback. This results in a slower system response with a significant steady-state error. These results highlight the natural dynamics of the system and demonstrate the need for a feedback mechanism to maintain the desired output. For the closed-loop configuration, two types of controllers were tested, a proportional-only controller and a proportional integral controller. With the P-only controller, the system's response improved significantly compared to the open-loop setup. The proportional action reduced the rise time and improved the transient response. However, the steady-state error was not fully eliminated. Higher gain reduced the error, but introduced overshoot and even sustained oscillation as seen in the simulation. When the PI controller was implemented, the system performance improved further. The integral action eliminated the steady-state error by continuously adjusting the control signal until the output matched the set point. While the rise time was slightly longer than the P-only controller, the response remained stable and accurate, with minimal offset and acceptable transient behavior. Next is limitation. The open-loop system cannot react to disturbances because it lacks feedback. Any variation in heat input or system conditions directly affects the output without correction, resulting in poor accuracy and drift. Closed-loop systems improve this, but have their own limits. The P-only controller reduces the error, but cannot remove it completely. Increasing the proportional gain too much can lead to oscillations or instability. The PI controller removes steady-state error, but improper tuning of the integral term can cause lag, overshoot, or even instability, especially in systems with delays. Last but not least, the conclusion. In this experiment, we analyzed the heated tank under open-loop and closed-loop control. The open-loop system showed slow response and steady-state error, proving the need for feedback. The P-only controller improved speed but left some error. Adding the integral action with the PI controller eliminated the steady-state error and stabilized the output. Overall, this study highlights the importance of feedback control, proper tuning, and understanding system behavior to design safe, efficient, and robust industrial process.